in part 1, if you remember when we talked about it, Fundamental Theorem of Calculus part 1 only says that differentiation and integration are inverse operations. They cancel their effect on the function. If we integrate if we differentiate an integral, we get the function. If we integrate a derivative, we get the function back. And we'd like to illustrate this with any function. Let's call it f of t. And here's t, and this is y, and we have a and b. And we know that this area is the integral from a to b from f of t dt. We know that. Now let's suppose we have x, and we have an x that takes values between a and b, and every time I plug in a value between a and b, what will happen here? So for example, if I look at the integral from a to x from f of t dt, what will this mean? Well, if x is here, it will mean this area. If x is here, it will mean this area. If x is here, it will mean this area. So what did we create? If for every x value we determine a new output, what do you think this is? What does it represent? Well, it is a function of x. So we can create a function of x in the form of an integral. We just did that. Why do we even look at this? We want to illustrate basically the differentiation and integration are inverse operations. So you see the upper limit is not a number. The lower limit is a number. This is a number, must be a number. This piece, the upper limit, can be x or a function of x. It can be sine x, it can be tangent x, it can be x cubed. At this point in time, we want to differentiate both sides. So we're not ever asked to evaluate this. It's a function. Unless you tell me x, I cannot evaluate it. If you say x is 5 and give me the function, I'll evaluate it. If you say x is 10 and give me the function, I will evaluate and give you a number. But with a function up here, I can never be asked to evaluate unless you give me the numbers. What we are going to be asked is to find g prime. So we are differentiating the left-hand side and we're differentiating the right-hand side. And the answer here is just f of x. Why? Because when we differentiate an integral, we get the function. And this is a function of x. So we differentiated an integral. So we got the function. And there are several applications for this. Let's look at a couple. And they come from page. Where are you? Yes, page 394. So let's look at a simple example like number 9. And we're given a function g of x, and it is an integral from, let's say, from 5, it's 5 to x, from t minus t squared to the 8th power dt, of course. We're only asked, since this is a function in a form of an integral, if I tell you 5, you'll say it's 0. If I tell you 6, you'll calculate. If we are able to determine this, we are just going to plug in the numbers. If we are able to determine the antiderivative. But we are not asked to do any of that. We are only asked to find g prime. So when we differentiate the left-hand side and differentiate the right-hand side, I make sure that this is a number, and I make sure that that is a function of x or a plane x. And then all I get is I get x minus x squared to the 8th power. I should write times the inner function prime. There is no need because this is 1.
So you replace the t's with the x.
That's all it's done. So when I differentiate an integral, all this disappears, and this is a function of x. If this is anything else but x, I would have to multiply by the derivative. But in this case, it was just a simple example with x up there.
I got you.
Let's look at 13. So you'll see what happens when the upper limit is a function of x, not just plain x. So this is a function of x, the integral from 1 to e to the x from natural log t dt. Again, we are only asked to differentiate both sides. So then we have h prime of x will be, when we differentiate an integral, we only get the function, but this time what we have to replace t by is e to the x. So this is natural log e to the x, and since this is not plain x, I have to multiply by the inner function prime. The inner function is this. The outer function is the integral. When I differentiate the integral, I get the function, but now I have to differentiate by the inner function. I know that this is plain x because we bring the power in front and natural log e is 1, and e to the x prime is e to the x. So this is the derivative of this function that is given to us in a form of an integral. Now what happens when the upper limit and the lower limit are functions is the following. So let's look at 59, and this is on page 395. And we have y equals the integral from cosine to sine, and this is natural log. I didn't want to choose a problem that I did last night, but it just happened. I'll try to avoid, so I can show you as many examples as possible. Okay, well, in this case, we can still differentiate, but this particular problem needs some work. This situation needs work, which means what? Remember one of the properties we said that the integral from 1 to 4 from f of x dx is the same with the integral from 1 to 2, let's say, from f of x dx plus the integral from 2 to 4 from f of x dx. We have to use this property here. We have to break this interval. And you can say, what interval? Well, you can look at it as being the interval between cosine x and sine x. And you're breaking it up in the middle, anywhere you want. You can put any number you like. So then y becomes the integral from cosine x to any number. Some students like 0. Let's put 0. Anything you want, 10, any number. Natural log of 1 plus 2v dv plus the integral from 10 to sine x from natural log of 1 plus 2v dv. We are almost there. One integral is set up the way we wanted it to be set up, meaning a number as the lower limit and a function of x or x itself as the upper limit. However, this one is not in that format, but it's not a problem. We know it's another property of the definite integral that allows us to switch the limits of operation, but we have to put a minus in front. So then this becomes negative, the integral from 10 to cosine x, natural log of 1 plus 2v dv, and plus the integral from 10 to sine x, natural log of 1 plus 2v dv. Now all we have to do is just differentiate two integrals. It's a sum of two functions if you want. So then y prime equals negative natural log of 1 plus 2 cosine x times the inner function prime. This is not plain, so the function is the integral. We are differentiating it. We are differentiating the integral goes away, but this is the inner function, so that's why it's negative sine x. And then plus, when I differentiate the other one, I have natural log of 1 plus 2 sine x, and of course times cosine x, the inner function prime. So all I have to do, and there is nothing else other than just put this in front and change the sign. So this is sine x, natural log of 1 plus 2 cosine x, plus cosine x, natural log of 1 plus 2 sine x. Any questions so far? Any?
That negative went away because you multiplied it.
Yes,
by
negative 1 and negative 1. Yes, exactly. Any questions? Any questions on these problems that we just looked at? Any questions? Okay, so the next topic that we want to look at is we do have two types of integrals. One that we just looked at, definite. Definite integrals are always a number. So, for example, the integral from 2 to 5 of f of x dx, whatever f of x is, will always be a number. It's definite. It has definite limits, if you want. Lower limit of integration, upper limit of integration. The second type is indefinite. The indefinite is a family of functions. It's not a number. The same with the most general antiderivative. No limits of integration. When we want to check, this we cannot. This we can. And you'll see in a moment how. So let's look at a couple of examples of how to evaluate, how to determine definite integrals. Okay, let's look at problem 9 on page 404. The integral from u plus 4 times 2u plus 1 du. As you see, there are no limits of integration. We know that the answer will be the most general antiderivative. We don't know how to integrate products. You will learn how to integrate products in Calc 2. Right here, right now, I will distribute. I have no choice. So this is 2u squared plus 4u plus 8u plus u, which is 9u, and plus 4. So 2u squared, 8u plus another u, and 4. And now we go back basically to section 4.9. Which function prime is u squared? And we know is u cubed over 3 plus 9. Which function prime is u squared over 2 plus 4u plus a constant c. Now, let me refresh your memory on the notation. So if we're asked to determine, which we just did for a function in u, if we're asked to determine the most general antiderivative for, in other words, find the indefinite integral of f of x dx, do you remember what was the notation? What was the notation for the antiderivative? And that was the reason why we differentiated from the very beginning in 4.9 between the two notations. Because if I'm given f prime, because integration and differentiation are inverse operations, the answer is f of x plus a constant c. But here I'm given f of x. So what would be the notation that we looked at the beginning of 4.9? Well, the answer is the uppercase f of x plus c. So this is very important because this really tells us that integration and differentiation are inverse operations, and we just get the function. Here, when we integrate a function, we get its antiderivative, which is uppercase f. Okay. Any questions? Okay, for the same, it's 17, I would like to look at the integral from 1 plus tangent squared alpha d alpha. So here I will get stuck if I don't remember one of the trig identities. Anyone remembers what trig identity is this? 1 plus tangent squared is secant squared alpha d alpha. And now from this point on, it's very simple. It's tangent alpha plus a constant c. But yes, without remembering that, it would have been slightly difficult to determine. Any questions? Any questions? Anyone? Anything for me?
No.
Okay.
I was just writing that down.
Okay. Is it clear?
Yeah. Yeah.
Okay.
So if you had did you have to put the plus C each time?
The most general, very good question. Here's why. Very good question. And let's go back to the previous example. When I was saying a minute ago that when it comes to definite integrals, we can check. Now you could say, show me that this is true, and I can. It's a very good question. Thank you for asking. I was going to show you on a different example. Well, why not now? So we claim that the integral from 2u squared plus 9u plus 4 du, we claim that this is 2/3 u cubed plus 9/2 u squared plus 4u plus c. And now you can say, I don't believe this, show me. And I will do just this. So I'm differentiating this side. So I get 2/3, bring down 3, subtract 1 from the power, plus 9/2, bring down 2, subtract 1 from the power, plus 4u prime is 4, plus c prime, which is 0. So then we simplify, and we get 2u squared plus 9u plus 4. Because when I differentiate the integral, this side must be 2u squared plus 9u plus 4. The c is absolutely mandatory for the indefinite integrals. That's why we wrote this. We're talking about the most general antiderivative, not about a antiderivative, just the most general antiderivative. Yeah.
Okay.
And the last section, and we will have a lot of examples from, is the substitution rule. Let me see where I'm at with the